the recording started. It's a pleasure to have here Yuhei. Yuhei is a leading scientist in the field of subseasonal to seasonal predictions. Actually, he did a lot of work on that, and he's here in Bologna because in the past days there was a meeting on WMO about the operational, how a range of the operational centers that contribute to this S2S forecast for the World Meteorological Organization. There are many centers in the world, and they establish some rules and well, things like that. And actually, he's giving the first seminar today that is more on kind of tools, information, what is good to use for this these predictions. And the second seminar, it will be next week, coming week on Monday. I won't be here, but there will be Andrea, for example, that is very much interested, because the second seminar is about the role of the surface fields in kind of health predictability in this time scales. So please, Yuhei, the floor is yours.
Thank you very much, kind introduction. Buongiorno. I'm Yuhei Takaya from Meteorological Research Institute of Japan Meteorological Agency. As Sudan said, I have been working on more than 25 years, I guess, on the seasonal and sub-seasonal prediction. Today I'm going to talk about the information-based probabilistic focus verification and predictability measures. This kind of new method to evaluate the subseasonal prediction. So I got one thing in the introduction. So now I had a meeting this week on the operational climate prediction under WMO, and I'm very pleased to have now we have the Global Pollution Center for the subseasonal to seasonal prediction. And also the idea is basically the many international organizations provide operational subseasonal to seasonal prediction to national mesh services around the world. So it's really good timing to have to start to explore the usability of the seasonal prediction. Recently, the WWRP started the new project on the application of S2S prediction. I'm also involved in it, that project. So let me shortly introduce myself. I'm a senior researcher of Meteorological Research Institute, and my research interests covers many aspects in the subseasonal to seasonal prediction, climate dynamics, monsoons, tropical cyclones, and atmosphere ocean land interactions. So next week I'm going to give a talk on the land atmosphere interaction. I'm a member of the WMO Standing Committee on Integrated Processing and Prediction System, SC-RIPS. I'm co-vice chair of this team, and also I'm a member of the WCRP working group on subseasonal to interindicator prediction, big SIP. And also, as I said, I'm a member of the WWRP S2S application for agriculture and environment. So you're very welcome to join, participate in the research project, including this stage. So today I would like to give you the new idea on the verification. Probabilistic verification of seasonal or subseasonal, any ensemble focus. So I'm going to start with some introductions on the predictability and information theory because we rely on the information theory for verifying the forecast. And I will explain the predictability from a viewpoint of information theory, and I would like to introduce information-based probabilistic verification scores and predictability measures. This talk is based on our previous papers published in the monthly weather review just last year. And yeah, the new paper is under review now in the Quarter Journal of Meteorological Society. I forgot to acknowledge my co-authors, and I collaborate with Professor Hide Itsuhiro. He's from Institute of Statistical Mathematics in Japan, and Kensuke Komatsu. He's working with me as a postdoc in as a research scientist. I forgot the name. Another new postdoc is working with now. His name is Dr. Ganesh Narashi. And I also collaborate with Dr. Kayo Koelio and Dr. Frederick Peters. So let me start now. So when we talk about the predictability actually is different from the predictability skill. So here's the definition of the predictability from American Meteorological Society Glossary of Meteorology. And they define as the extent to which future states of the state may be predicted based on knowledge of current and past states of the system. So this is not, if you read this sentence, it's not the predictive skill of any particular models, but because of the chaotic nature of the system, we have just only one realization, and we don't know the possible uncertainty in the climate systems. So usually we use the model to assess the uncertainty. So sometimes the people use the predictability as a predictive skill, but the definition is different. All right. Then, so how we can assess the uncertainty of the forecast? Because the climate system is chaotic, so we use the ensemble technique. So ensemble technique is basically we use the deterministic forecast, but we create multiple members of the deterministic forecast to assess the future state, uncertainty of the future state, right? Then usually we consider the uncertainty of initial condition and model uncertainty. Then we can assess the focus uncertainty. Then this idea is really related to the Liouville equations. So if we have if we have the dynamical system like these equations, basically the x state is state variables and f is the function, then we can predict or we can compute the future state, right? Then the time evolution of the predictability, rho is predictability of the state vector x. X can be a very large dimension. The variables of large dimension and t. Then we have the new equation like this. So the future state of the predictability is we can write it exactly using the function f, but we don't know the function usually, exact function of the climate system or real world. And I requested that the predictability neither vanish or invanish. If we look at this function, actually the time evolution law is propagated by the f. So this is similar. Actually, we do the solve this equation using the deterministic many numerous ensemble predictions. Then let me explain because I see some PhD students here. So let me explain about the chaos. The chaos. Okay. Ed Lawrence discovered the chaos. So chaos is even we have the deterministic system, the small difference of the initial functions can create a large diverse consequence in the future. Right? Then he demonstrated with a very simple equation written here. We call the Lorentz equation, and you see the very simple, but there is a nonlinear terms here. So then, if we solve the equations, basically this is a solution in the space of x and z, and actually we see the solution like this, right? Then if we start from here, then the future state may be not that different in the future, but if we start something here, then we could have a large difference. So actually, the future uncertainty is depend on the state of the initial function. So that's why we use the ensemble prediction. And actually, in 1965, Lawrence wrote this document. This is a proceeding from the proceeding of WMO IUGC symposium. At that time, of course, we didn't have the ensemble prediction system, but he exactly stated that like this. For the sake of time, I don't read, but exactly he said if we can use the multiple ensembles, then we can get the future uncertainty using them. Now we call the ensemble prediction, right? So it's surprising because this was written 30 years ago, before the operational ensemble focus commenced. Actually, the ECM Davet and NORA started in late 1990. So yes, this is kind of surprise when you read the text. Then, okay, because the nature is very chaotic, how can we get some sort of reliable focus information from the ensemble system? So here I quoted the sentence from the book of Monsoon Dynamics. This is written by the Chang and Shukla 1981. And basically, the Chang and Shukla stress that on the basis of the available evidence, it is suggested that a large part of the low latitude variability is due to boundary anomalies such as sea surface temperature, albedo, soil moisture, and so on. So these kind of boundary conditions give the sort of predictability in the extended range or subsequent prediction and season prediction parameters. So it's surprised that they know that, okay, at that time we know that the sea surface temperature later, albedo is the snow property and basically and other property. And they notice that the albedo and sun motion has a large impact on the predictability in the longer time range. Then Professor Tim Parham, probably you know of Oxford University, explained this idea using very simple equations, again based on the Lorentz equations. So if we, as I said, the Lorentz equation is a chaotic, has a chaotic behavior, but if we put the additional forcing, external forcing, then the solution in the future is the probability of the solution in the future actually shifted a little bit. Then we can create the seasonal prediction or sub-seasonal prediction. Right? Please feel free to interrupt if you have questions anytime. Let me explain, give a background of the information theory, because in this talk I would like to explain how the information theory is related to the focus predictability or focus uncertainty, right? I don't know how you're familiar with information content or information theory. Information theory is originally the mathematical idea that comes from the telecommunication but nowadays this is a basic mathematical idea, and we can apply the information theory for any fields. Right. Then here I would like to start with self-information, or known as the information content. The information content is defined as like this. The P is the probability, and log is a logarithm function. And here I'm sure use the log 2, so the unit is a bit. So, for example, if we have the event if we have the dice and the probability of odd to have an odd is the probability is 0.5 or 50%. So the information content actually is 1. But if we think about the event 1, then probability is 1/6. Then the number is like this. It's larger than the information content of odd. So we have more information if we know we have the 1 when we through the dice. So knowing the occurrence of a rare event means gaining more information. So if you can predict a rare event, then we have the more information.
Can I tell
Yes.
you? So basically, if I had X in the ensemble odd and even, then
there's no information.
No information, so it will be 0.
Yes.
Okay.
Yeah. Thanks. Yes. So probably if you look at these definitions, you can understand what this equation measures as in the content of the information. Right? Then we can also think about let me explain the characteristics of the information content. So because the information content is defined as this, the information content is non-negativity. It should be greater than and equal and greater than 0. And if we have the independent event, the information content is the summation of each information content of each event. right? So if we think about the x and y, and if the x and y occurs randomly, then the information content of xy is the summation of ix and iy. So this is a really good property of the information content. And yes, so the information content is 0 for certain event like the odd even event. And the information content increases as probability decreases. So again, knowing the occurrence of a rare event means gaining more information. And here I'm showing the example of the entropy. Let me move on to the entropy. Entropy is the average information content. So if we think about the 4 categories, and for example, if we have the probability of the first category is 0.25%, and second one is 0.5, and third one is 0.25, and the fourth category is 0, then the average of the information content can be computed like this. Then the number is 1.5. Right? Then, if we have even probabilities for 4 categories, so all probability is 0.5, then the number is 2. So if we compare these 2 numbers, we see the larger number here. So larger number means the information means more uncertain. These probability are more uncertain than the probability.
So basically, sorry if I interrupt you. So that one is more or less like a Gaussian distribution.
Yes.
So Gaussian distribution has less entropy than a flat distribution.
So if we have a flat probability, that means we don't have less information because we don't know each category can occur. So this is so the entropy is the measure of the uncertainty in our work. Right. Yes. Okay, we can also think about the continuous entropy. Here I show the discrete categories, but entropy can be defined for the continuous probability density function. So I show the normal distribution. Then analytically we can get the entropy, just integrating for all possible outcome from minus infinity to infinity. Then we get this one. So if we have the analytical form of function f, then we can compute. Let me explain further on the Karlbach-Driver divergence. You may know or not, the Karlbach-Driver divergence for relative entropy is a measure of how one probability distribution diverges from the other. So, for example, if we have the probability function of P and Q, the Karlbach-Driver divergence is defined with this equation. Okay. Then, okay, if we have we know the probability density function is a 2 Gaussian distribution, we can exactly have the equation like this. So we can have analytical form of Karlbach-Driver. This is just to illustrate how Karlbach-Driver divergence computed with the 2 normal distributions. So if we have the same probability function, so the difference of the, by the way, the mu is a mean, and sigma to the process for is squared sigma is divergent variance. Then, okay, if we have the same distribution, the carbon divergence set here. And okay, here I'm showing the difference. If we have the mu equal 0 and the sigma 1 equal 1, then we can have the carbon divergence like this. So far, we consider analytical form, but when we produce the ensemble predictions, we have to compute the carbon divergence or information content using the ensemble prediction. So I thought about how we can compute this property using the ensemble predictions. This slide basically explains how we can compute the information content. So in the probabilistic verification, there is a score proposed previously known as a ignorance score or logarithmic score. And the logarithmic score exactly defined as a no. I swear I didn't put the definition of logarithms. So I forgot the one slide. Anyway, so we proposed that, so we named this score as a fixed radius neighbors ignorance score. I'd like to explain how we can compute. So here I'm showing the ensembles, and the orange circles are the ensemble prediction, and the blue circles are historical observations. So we have the PDF of climatology, and we have the L-shaped probability distribution of ensemble prediction. We can just we can use kernel to produce this kind of probability. So then, as I said, we have only one observational difference for the outcome. So the red cross circle is observation for difference. So then we can assess the predicted predictability probability of the ensemble prediction by using the near-neighbour ensemble. So if we set the distance from the observation reference, here I use R, then we can count how many members actually fall in the distance between these this range, right? Then we get the number, the KF. Here I use the KF for the number of ensemble members within this range. And also we can compute we have a total number on some side. So basically, the Kf over Nf is a probability in this range. So, and Vx here, I showed a spherical volume, but actually, if we consider the one-dimensional variables, the Vx is just a distance of 2r. And this expression is very, actually, very similar.
Yep. Observational reference is the verification analysis.
Yes, verification. So if we have more ensemble members in this range, then we have the larger probability. Right? And so this is very similar to the Kozachenko-Leonenko entropy estimator. This is an estimator for the entropy, but if we think about one information content for one outcome, then exactly it is the same, except for the I simplified function using the logarithmic function. The Kozachenko-Leonenko entropy estimator actually uses the gamma function. It's slightly different from the log, but basically the calculus is the same. So I just simplified using the logarithmic function. So this is how we can compute the information content around the observation or verification. Then, based on this equation, we can compute the scores. This slide shows the scores, how these scores looks like. So on the top, I showed the fixed radius near neighbor ignorance scores for 2-meter temperature in summer and winter. On the bottom, I showed just continuous ranked probability score. Probably you are familiar with this score. This is a very used probabilistic verification score. And basically, we see a very similar spatial distribution. That means these two properties very similar. And also means this new score works well to assess the focus Q. Right? Of course, the number is different. But basically, the spatial pattern is very similar. And here I use the no normalization. So I just compute the score using the low number. But probably you can notice actually the score depends on the unit or the scale of x. For example, if we think about the temperature in Fahrenheit or Celsius, the number is different because in definition we see the integral here. So if we use the x as a Celsius in Celsius or Fahrenheit, the value is different. So to avoid this, we can normalize the temperature, for example, in this case. And before computing the scores, we can normalize temperature using the standard deviation of observed value, climatology. Then the results looks like this. By the way, this is a focus Q using the each number.
Can I interrupt you? So, in a way, if you look that a good score, how can I know if the score, how good is the score reading the numbers?
I will explain.
Okay.
Sorry.
Sorry,
Yes.
I'm a bit impatient.
I have to say, here the smaller number is better for this. So we see the yellow color in the tropics and the blue color in the polar regions. That means the skill in terms of this score or CRPS is better in tropics.
Sorry.
Yes.
Another question. How do you choose? How do you decide the value of R?
Yeah, that's a good question. The number of R should be defined somehow. And for example, if we think over here, I suggest 0.25 standard deviation multiplied by 0.25 for this substitute equation. I tested I tested the many calculations based on the idealized experiment, and I found that 0.25 is a reasonable choice for R. Of course, it depends on the skill. If you have a very good focus system, we can reduce the number the R because basically we have more ensemble members close to the
So R must be a fraction of the climatological, of the radio of the climatological distribution. In a way.
Shouldn't be, but it's easy to scale, choose the number using the standard deviation. Yes. For example, actually, if we think about the verification of categorical probability forecast, probabilistic forecast, we often use the tercile. That means the three categories. But if we have more accurate or ensemble, we could have the quintile or n numbers. So if we increase the number of the categories, that means the decrease of the target categories. So they are similar numbers as a number of categories. So it depends on the skill. So here thank you. I use the standard deviation multiplied by 0.5. Then the result is like this. Okay, let me. This slide shows the normalized fixed radius near-neighbour inverse curve. We see more green yellow curve here, and we see the blue curves, but without normalization, we see a very distinct value in tropics and subtropics because of the variance are quite different in tropics or exotropics. But if we normalize, the difference, regional difference reduced, so the figures are like this. Again, I'm showing here the information ignorance score and CRPS. They look very similar. Any questions? Okay. So yes, we want to know this value is meaningful or not. So the baseline could be the climatological forecast. So the previous studies okay, suggested another score. It's the gain of information, information gain. The information gain is defined by the information ignorance score of parameters forecast minus ignorance score of uh, model forecast. Then we can assess how much we can gain this skill in terms of the information form. So basically, the computation is straightforward. We just compute the same information ignorance score using the same equations, and we can apply the chromatographic forecast and sample prediction. So we can compute the information gain. So information gain is the measure of how much we can gain. We can have the benefit using the dynamical mode. Yeah. So, okay, we can compute the information gain. Here, this is the same as I shown in the previous slide. And on the bottom, we see the information gain. So information gain is if we have larger information gain, that means we have more gain in terms of the ignorance score. And we see that darker color is a larger value in tropics. By the way, this is the results for tropical temperature for summer and winter. As we expect, we see a large value for the central and eastern Pacific because of EXO, the good high predictability of the answer. So, yeah. And if we look at the results of summer, actually we see a larger value in the subtropics and tropical Atlantic and Indian Ocean. Actually, I did some research on the predictability of Indian Ocean or Atlantic. They show the good predictability in summer. So this also indicates that we can have the source of predictability for the season predictions from these reasons. Yeah.
Is there a reason why the summer plots are more granular?
Oh,
They
yes.
are. There are more details.
Yes, it's a bit noisy. I have clear explanation, but the scores can be very noisy if we assess the season prediction because of the limited number of sample size. So for season prediction, we only have 30 cases or 40 cases. So using the 30, 40 cases, we could have a bit noisy verification scores if we look at the values on each grid. By the way, these results for the 2.5 degree grid. But if we compute a 1.1 by 1 degree grid, then we see more noise. So if we average a certain areas, we could have more smooth value. Yeah. So, sorry, I forgot to mention. So we can compute the scores for each case, and we average the information ignorance score or information gain for all cases. For example, if we evaluate the 30 years we can compute the value this for each year, and we arrange the scores using the 30 cases. So, because we can compute the scores for each case, so we could use this score for assessing the conditional prediction skill. So here I'm showing the conditional prediction skill for tensor year, tensor winter, and La Nina winters. On the right, I'm showing the scores for mean sea level pressure. On the left, we have the 2-meter temperature. Okay. So we can notice that the difference between the El Nino and La Nina. In terms of the ignorance gain, we found that the scores are larger for El Nino than the La Nina. This kind of surprise, but yeah, in terms of the ignorance information gain, I think this is the result. And we also noticed, we can see that the red curve over Indian Ocean, but we don't see the this red curve in La Nina case. So yeah, actually in El Nino winter, we could have a better forecast over some basin, including Indian Ocean or Northern Pacific, right? So we can use this kind of this skill to assess the conditional prediction skill. And we can compute the scores for any variables. So I'm showing the example of the mean sea level pressure, and we also see that the red curve in El Nino winter than La Nina. So in El Nino year, we see the red curve over North America. That means we could gain some focus information of the skill because of that over US or China. Intuitively, yeah, it's reasonable, but when we talk about the predictability from El Nino or ENSO, we just mix up. But actually, the skill gain is different for El Nino and La Nina. It's good to notice the difference. Let me show some example using the entropy. So, as I said, I didn't explain. So we can also define the entropy using the near-radius, fixed radius near-neighbors method I explained before. So the definition is same. So for entropy, using the ensemble members, we can take one ensemble member as a surrogate observation, verification, and we can compute the information information content or ignorance score, and we can average the all surrogate ensemble members. So if we have the 30 members, we can take member 1, member 2, member 3 as a surrogate observation. We can compute the ignorance score, and we can average. Then we can know the uncertainty using the ensemble prediction. So here I'm showing the entropy as a measure of focused uncertainty. The figures is quite similar compared with the information ignorance score. So we see the yellow curve in the tropics, in entropy, in ensemble. We see the yellow curve in this area. So if we compare the actual focus scale and entropy estimated by the ensemble member. It's a kind of idealized estimate of the uncertainty focus scale based on ensemble predictions, and we got this. Some area we see the larger differences. For example, here, actually, this is because of we know that the model often have the excessive extension of the core time area, and if we have the more variability here, and actually the actual scale is worse than these estimated predictability based on the ensemble. So these figures tell us where we can improve the model. For example, as I said, we also see some difference here in the ocean. So we assume that the model is perfect when we compute the entropy. So yeah. So this area could be improved if we have more reliable better focus model. Ideally, we do the same party if we have a perfect model. And we can also compute the relative entropy. Relative entropy is very similar to the ignorance gain. We just use the ensemble members as a surrogate observation. We can compute the ignorance gain, then it's a relative entropy. Again, if we compare the two figures, figures looks very similar. That means actually relative entropy is a good measure in terms of the information gain. Measure of focus uncertainty in terms of information gain. So we have to appear of the focus uncertainty measure and actual focus score. That it's very useful because we can compare the both using the information-based method. Finally, here I'm showing the rank correlation score between the information ignorance score and entropy. Right? Yes. Ignorance score and entropy. Here I use the value of the scores for each case, and we can compute the rank correlation for time series. The result like this. The reason why I did this analysis is so if we know the uncertainty of the ensemble focus, and in some cases we have more confident, so ensemble members actually correlate is close to the certain range, then we can say the focus is more reliable or certain. If we have very large, we use the spread usually. So if, for example, if we have the large spread, the focus is more uncertain. And small spread means less uncertain. So we can do the same thing using the ignorance score and entropy. So the red color means we can know how the focus is reliable in terms of the information-based prediction. So this is good because okay, if we compute the entropy for each case, then we can know how reliable is the ensemble focus is. So it's good. What's the difference? Okay, we could also compute the same thing for ignorance gain and relative entropy. And we see the more red color in the tropics because of the characteristic of ignorance gain score. So in tropics, we can use the ensemble to measure the uncertainty of the ensemble focus. I'll shortly introduce this score can be defined for the two-dimensional variables or three-dimensional variables. So here I'm showing the example for the assessing the M0 score. Probably you know that we often use the M0 index, which is a principal component of EOF 1 and EOF 2 over tropics. And yeah, we often use this kind of type. And okay, the circle is the focus at various lead time. And so if we start from here, in this case, M0 pocket, and yes, ensemble members they are part in longer times, longer lead time. Again, we can define the ignorance score as like this. In this case, the volume V is the area of the circle, and we can count the ensemble members, and we can compute this.
Sorry, so basically that one on the left is the PDF in 2 dimension of how the ensemble members are distributed in this 2-dimensional space.
Yes. But
okay, and then in black you can have the
observation
verification, the trajectory.
Yes.
Okay, so then you apply your scores in the 2-dimension. So okay, I was just trying to. Because it's the first time that I see the application of this score in.
And color shading is climatology. And yes, actual distribution is like this. The blue is all climatology, model climatology. And we can count the number in the circle of the radius r. This figure shows the ignorance gain of M0 index with respect to the lead time, day. Of course, in long lead time, we have less skill. So the ignorance gain is declined like this. But it's good. The initial document. By the way, this is results of E-semi-perfect model in the SPSR type. We see that still the inverse gain is high. Is above 0, means the focus model is better than the current also.
So
yes.
The quantile,
quantile
might be like an uncertainty
yes.
in the score. So basically, if I understand correctly, I have a certain gain up to day 25 or so.
Yeah.
Basically, when actually the uncertainty is still higher than 0.
Yes.
Okay.
So this is kind of confidence. So quantile is a quantile of this score, because this score can be computed for each case. So, for example, in this case, we have a large number of cases, 700 cases, and the blue color shows the quantile of the scale. And again, we can use the conditional prediction scale. We're interested in how the answer phase for the initial MTL phase can influence a focus scale in terms of this score. So here I'm showing the first, I'm showing the difference among the MTL phase of initial date. And x-axis is the lead time, and y is the phase. So, for example, if we start from the phase 4, 5, then yeah. So we see the more information gain. That means the focus is better than the current, or more, even better in this time range compared to the current order focus. But we see the less good in this time compared with the average of all phases. So actually, the M0 focus skill depends on the initial phase. There are many papers discussing about this, but there's no conclusive results. But results in this particular model, we got this result. Also, we can compute the difference between for linear function in this case. We checked the linear case, but just we found that more impact in the linear case. So I'm showing the focus skill difference between linear year and all years. And in linear years, we have more skill when we start the focus from phase 5 to 6, like this. Because we know that sometimes model struggles to represent the MGO crossing the maritime continent. And yeah, sometimes in linear, that propagation can change. So that's why you see some difference.
Sorry, I interrupted. Have you looked at this score also in terms looking at the NAO, for example? So just conditioning the predictions of MJO to so double conditioning in a way. So let's say La Nina and a certain phase of MJO to see if the prediction of NAO are correct.
So yeah, I hope the more studies. Hopefully, you can use anyone can use this score and evaluate the conditions like AO or any condition. So this kind of tool to investigate the conditional skill in terms of this score. So summary so far. So I hope I could convince you this score can be useful. And score and also we can define information-based predictability measure or focus uncertainty measure using the same concept based on the information theory. And these measures of predictive skill and predictability for useful for analyzing the ensemble prediction or analyzing the conditional predictabilities. Yes, there are many applications using this concept. Lastly, I would like to give how this measures related to the previous uncertainty measures. Here, I would like to explain the relation between the Lyapunov exponent. Lyapunov exponent is so the time evolutions of the predictability or the departure. So yeah, but basically we can define these values, which means how rapidly increase the departures with time, focus time. Actually, this measure is also related to the talk the next week. So, as I explained, if we have a dynamical system like this, then we have Yuhei equation like this. Actually, with some mathematical calculations, we can derive the entropy of time evolution of entropy as like this. So if we have deterministic for, by the way, if you are interested in the proof, you can look at the paper. It's not that difficult, but we clearly show that the entropy is divergence, expectation of divergence F. So if you think about the figure like this, the F is okay, the equation to the function to describe the time evolution. And if we have the circle around certain initial function, that can be expanded in the future. Maybe it's better to explain using this figure. So if we start the ensembles, for example, this area, the area can expand, okay, in time. So exactly the entropy can be written, time evolution of entropy can be written as an expectation of divergence of F. So it's so if you think about the linear system, actually divergence F is a kind of Jacobian. The Jacobian is the area change because of the function F. So yeah. So entropy is not it's not just a mathematical property. Actually, it's really related to the physics. I mean, there's a physical meaning of the entropy. If we think about the equation. So yeah, to conclude, yes. So I propose a measure of the focus to probabilistic verification and predictability. This is really closely related to the concept of the entropy of the dynamical system. So that's why I think it's useful. It's not just empirical measure. This is really derived from the physics or equations. Okay, and yeah, I'd like to explain the next part in the next seminar. Actually, they here, Professor Sandia and Jeffrey, they discovered we can derive the time evolution of entropy based on the equation. So this is a very robust theoretical thinking about the predictability. And more, okay, I will explain that next week. But yes, we can use this kind of technique to analyze the causality in terms of the information content or entropy. So to conclude, the information theory is an essential concept when we consider the predictability in dynamical system, and its applications are expanding in many areas. And we could use this mathematical concept for verification, for causal analysis. And average of information content in dynamic system provides an information theoretic interpretation of predictability. By using the proposed information-based probabilistic verification score and predictability indicators, we expect that predictability in ensemble focus can be discussed consistently. So we can combine the results of causality analysis, I will discuss next week, and this actual predictability or predictive skill. So I hope you are interested in these kind of things, and I hope you enjoy the talk. Thank you.
Thank you. We don't know, before there were some people connected, but if people connected have some question, please speak up, because we don't see you in this mode, but yeah, so speak up and say, I want to do ask a question. About that, if yes?
Yeah, can you speak up?
Yeah, who is speaking?
It's Jost, actually.
Jost. Yeah, please.
Yeah, it's quick. Yeah, thank you. A very, very interesting talk, and I appreciate it a lot. Thank you a lot. I was curious. It's a question I actually had already after the initial introduction. I mean, apart from, which is this type of skill scores. How do they compare to other classical skill scores, which are usually used in the community to evaluate seasonal forecasts? I mean, they all look at different aspects of the prediction. And so I wonder, in this case, what are we looking at? Or is this really one gets it all comprehensive measure, which you would recommend in all cases? And I mean, usually we are used to use several different scores because each of them looks at a different aspect. And so I wonder where this type of score is.
Yes, this score is based on, as I said, the information theory or information content. It's a mathematical theory to describe the uncertainty or, yes. And the other scores, probably you're talking about for example, CRPS. CRPS is the integral of the square difference of the probability. So the CRPS is a kind of extension of RMC for the deterministic forecast. Okay, the CRPS is a good score, and actually the CRPS is a kind of simplification of the entropy or information content. So yes, these are very similar. even the equation is different. I believe that this score can be one complement for existing scores. And actually, the CRPS is widely used probabilistic scores, but there are very few for assessing the verification of continuous, for probabilistic forecast. We have several for categorical forecast, like we have the rank probability score, or prior skew score, or log scores. We have several. But for if we assess the overall skew of the probability score, maybe CRPS is just one score widely used in our community. And that's why I want to propose a new score. I believe that this score can be also used for assessing the verification. Still, I don't know which is better, or I don't say our score are better than the CRPS, but we need to investigate more the characteristics of the scores and how the results are different. So still, we need more work to underpin the benefit or advantage of the new score. I hope I could answer.
Yeah, thank you. May I make a second question, actually, brief question? This is a continuous measure. I assume that this cannot be applied instead to categorical forecasts, right? So where you evenience or not evenience of an event.
Mm-hmm.
Say going over some threshold for an extreme or something like that.
Yeah. I haven't thought about it. Oh, sorry, I don't have answer now. Yes, it's good to explore the information-based score for exceeding probability. I haven't yet done. Yes. I am aware that there is one study proposed the ignorance score using the exceeding probability. So if we think about the cumulative probability function, like the CRPS, we can also compute the ignorance score using the cumulative probability function. And there is one paper. But it doesn't solve the problem. I forgot one thing. Yeah. I should explain. When we compute the count the ensemble size, sometimes we have more ensemble members between in this range. Then, of course, we have 0 for KF, and we can define this score. In that case, we can search the nearest ensemble members, and we can just little bit expand this range, and using the new R to compute this score. Then we can have the number, even originally we don't have the ensemble size in this range. Because because of these definitions, we could have the divergence of the score. So basically, this number can be infinite. So, this is one trend when we try to use the logarithmic score for categorical forecast or continuous forecast. Previously, the ignorance score was proposed around in 2008, but it's not very used because of the characteristic of divergence. So if we want to apply this the ignorance for categorical forecast, sometimes we have 0% if we compute the probability. And if we have the 0% for the outcome of realized outcome, then we don't have the number. We have infinite number. So it's not very used. It's not easy to use. So sometimes the people put the small probability, even the ensemble member doesn't predict that category to avoid value. But if there is an arbitrary choice of the probability, it's hampered to apply the logarithmic for the category forecast. In this case, we avoid that problem because we use the near neighbors computation, then we can avoid that problem. Yeah, consistently.
Other questions from space? I hear some.
I have a question. I thought it was interesting that you showed the gains overall of the CMWF seasonal system. And I had two questions. One is if you had tried other systems falling into the Copernicus C3S, and if it has the same pattern overall.
Yes, to some extent.
Okay.
Okay, ECMWF is basically the best system. So we see basically we have the positive number here. The purple color shows the positive numbers, and orange color is the negative numbers. Overall, we see the positive number. That means the model has an added value or added skill compared with the planet performance. That's all. Yes, if we look at the other system, also we see some difference, but basically we see this very similar spatial pattern. Of course, the value is different.
Okay. And another question, you've shown that with distinguishing La Nina and El Nino, you had these results. I was wondering if you had looked at intense El Nino and La Nina or any Nino.
I just used the traditional definition of El Nino and La Nina. It's, so the Nino 3.4 SSD about 0.5 something.
All right. Thanks.
So yeah, I didn't use any special. So yeah, we know that the amplitude of El Nino, the amplitude of anomaly in El Nino cases are larger than La Nina.
So there are distinguished patterns even taking any.
Yes. But clearly we see the difference of the spatial pattern. Actually, we know that the teleconnection is slightly different between the El Nino and La Nina. So there is a symmetry in the isotopic to the teleconnection pattern. That probably can explain some difference, but mainly probably the response of the atmosphere to the surface temperature is much stronger in El Nino cases than have the stronger influence for predictability gain in terms of this.
And then I have a couple of questions. The first one, I was wondering if you kind of look at the sensitivity of your scores to the number of ensemble members that you use. Well, if it is more or less sensitive with respect to some other traditional, like the continuous random probability scores.
So this score also depends on the ensemble size. So basically, the score gets better when we have the larger ensemble as other scores. So there's no, yeah, I would like to have the unbiased score with respect to ensemble size, but I haven't yet found the solution for this score. Yes, in previous in this paper, actually, I show the sensitivity of the ensemble of the score with respect to the ensemble size. Probably it's difficult to share now, but yes, if you are interested, please look at this paper.
And another question is related to the different length of forecast, because of course in general the score that you can apply depends on the ensemble size that you have, but also on the number of verification points, basically. And I remember that one of the main problem in applying the probabilistic, in general probabilistic scores to, for example, multi-annual or decadal forecast was that you don't have main independent verification. So basically, you can expand the ensemble size, of course, but the number of verifications cannot be expanded. So I was also wondering if you think that this kind of score could be applied to, for example, decadal forecasting. Yes. And do you know if it has been already applied? No. Because that, well, and also I was just brainstorming now, so it's not, probably I might say something not really meaningful. But for example, I was wondering if this could be applied in cases of potential predictability.
Yeah.
So basically, and that you don't have anymore the limit of the number of verification, because of course it's potential predictability. So you use one ensemble members and to look at the others, and then kind of in terms of, and then you could basically map the have a map of the potential predictability, different lead times of any places, at any grid points. And since it's based on entropy, actually it gives you, can give you an information about actually the potential predictability and the idea of how chaotic is kind of given point in the tractor. And also you could also map in terms of the time. So for example, if you have different realizations, but in different, as you, for example, you did with El Niño and La Niña, so basically using the probability under these two cases, one could do the same with, for example, looking, for example, at the climate change when the CO2 was lower and the CO2. And since now there are a number of large ensembles, so large ensembles, climate, large ensembles in the historical periods and also in scenarios, one could actually look at how the predictability can change with the climate change. And well, what I like of this is actually it's the physical meaning of the score, which is kindly very well connected with the very concept of entropy. Well, that's some consideration that
exactly. Yeah, I plan to do that. Oh, actually, but I don't have time. Yeah. So yeah, if you are interested, I'm very welcome.
Well, I was because a colleague of mine Alessio is not here because he had another meeting, could not. But I know that he made an experiment of decadal predictions with a simple model, with an amic model. Actually, this is the model. I don't know if you, Speedy, do you know it? Because it's the model that was developed by Franco when he was at ICTP, and now has been further developed by ICTP and has been coupled with NEMO. So basically, he used this kind of amic model and coupled with NEMO to do seasonal decadal forecast. Decadal forecast with a huge number of ensemble members. I don't remember now. And I was wondering if one could actually do some exercise, taking advantage of having many ensemble members and look at different periods or even different years in a way.
Yes.
Yeah.
So this score is just basic score. So you can apply any ensemble prediction, extended range, short range, even mesoscale ensemble.
You didn't. You should only the results on S2S from. But you did apply to different lead times.
No yet. So,
not yet.
Yes.
Okay.
So that's why I'm planning to apply this score for the subseasonal prediction because the conditional predictability is one of the topics in the SAGE project.
Yeah.
So, I plan to that. If you are interested, I'm very happy to collaborate because now I see many young scientists.
Yeah, well, we will discuss about that. And then if you are around also on Monday, if you see someone.
I haven't thought about decadal prediction. One challenge of decadal prediction is that, as you said, we have very limited number of the sample size. In addition, we have the correlation of cases. That means that we have the less free number of freedom. So even we have the less samples. It's very difficult. I would like to say this score is not depend on the ensembles sample size, the number of cases. But of course, if we have more sample cases, then we could have more robust estimate of the score. Score is not very sensitive to the sample size, but the robustness or the confidence is related to the ensemble size.
Okay.
Sample size.
Well, I think I don't have any other. If someone has some other questions, otherwise.
Because I heard some people working on the regime, or yes, we can apply this technique for any condition. The study of any condition. Condition. So very fast.
So, for example, because actually we have a project in which is related to the predictions of, it's a long chain, but the main at the end, the goal we have it is a project with colleagues in hydrologists and of course they are interested in the predictions of floods, basically in some places in northern Italy, in the Great Alpine region. And one of the ideas was just to try to see if the knowledge of the circulation regimes could lead to a better prediction. So, of course, there are many pieces of this chain because basically, first one has to see if actually these extreme events can be kind of related directly to some circulation regimes, and then one has to
Yes.
To see the prediction of the regimes, but the idea was also to look at the future, so the future in terms of near-term climate change or long-term climate change, so the mid-century or the end of the century, if the frequency of these regimes change, how these changes can translate eventually in a change in the floods, or in some way, and how this can be. So maybe this can be a way of
Yes.
applying some
Yes.
call that. So there is already someone doing that with the regimes? No.
The paper is under review, so
okay.
No. Honestly, the most part actually is presented in the paper. It's under review now, so hopefully we get accepted.
It's under review in monthly, you said monthly?
No, quarter is not.
And the quarter?
Yeah.
Okay.
We have the paper on the MGO.
The one that
monthly
you
with the review, but other part is under review. And related to your question, so if we think of the dynamical system, and if we think of the hydrological application, we have the combined atmosphere and river line. We can have the equations to describe the combined system. So we could actually, this F can be a combination of linear function. In simple case, that we can just compile the linear operator. Then actually we can assess the entropy of atmospheric fields or precipitation. Then we also have the linear operator of the hydrological model. So in theory, we can disentangle the propagation of predictability or uncertainty in the same form. I hope to explore more the kind of things, explore how the forecast uncertainty propagate to the
propagated in another
another component like the ocean atmosphere. And the uncertainty of the atmosphere can provide that is interactive. There is an interaction between atmosphere and ocean. We could have the uncertainty because of the atmospheric component, because there is interaction. Yes, this kind of things I haven't yet done, but yes, can be done in the future.
Good.
Yeah. Many things. I have many ideas. So if you have time, I'm really keen to collaborate with you. I want to have students, but
it's a bit can be interesting. Well, the main problem of our group is that it's not small. It's not too small, but we are kind of I would say spread thin on many different streams, and you might know the problem because there are different projects, and of course we have to apply different projects of European Union, and we cannot not apply because basically the external projects are our main subsistence in terms of money to get people, to get PhD students, and so on. So it's sometimes you know you have the same problem. I guess because it's a general problem in every country. I would say so. Maybe in Italy more because you don't have many fundings, but I think so. But that's and it might if you have Actually, I think that if one could try to apply already the algorithm to some kind of different kind of predictions, and also, well, I think that it would be really interesting in looking at potential predictability of different systems and see. And also maybe have you thought of also applying something like that? That the problem of what's called but now the North Atlantic paradox.
Yeah. Signal
So,
noise.
Yeah.
yeah.
Signal noise paradox. Yeah, it's
Yeah,
really
yeah.
good
Thank you.
question. It's
In the North Atlantic.
yeah, based on the variance analysis.
Uh-huh.
The variance analysis basically assumes the system, the distribution for the Gaussian distribution. Sometimes we forget that there is a very strong constraint. And the system should be Gaussian, follow the Gaussian distributions. And based on that, we can compute the variance, and we can really do the number operation. But if we have a skewed score, of course, it's not theoretically, it's not necessarily have the so it's not paradox. It's a mathematical theory.
Yeah.
But yeah, very interesting. I haven't looked at the signal noise paradox in this context. Of course, we can compute the potential predictability using this score. We can compare the actual scale and how.
Yeah.
It's a very interesting things. Yeah.
Good. I think